Wow, so I have a topic that could be as big as the universe or it could be small, but you asked me for physical augmentics, so what I thought I'd do is trace out a bit of the history of physical augmentation and then selfishly and hedonistically talk about my research a little bit because I think it's fun. And you can throw things at me if you want. But I wanted to put up an initial slide to talk about what all of this means, and there really is a broad spectrum that's really important. There's mechanical devices that make you do something that you could not otherwise do. There's maybe this issue of electronics and how electronics or motors and sensors can be used to help this process. And then of course there's the idea of rehabilitation, which is I think a very big thing. It's what pays my bills because I work over at the Rehab Institute. But then also the idea of maybe even augmenting at a distance the behavior of humans. So this is actually the NASA robot, and I would say something provocative now, which is I think space exploration, the real role of space exploration is physical augmentation, where humans are really present but not physically present, but instead projecting their presence over a distance. Nobody dies.
So hoping to get in my frequent flyer miles.
Exactly. So I don't know if I don't know if you've done any sort of introduction about what's going on over at RIC.
No.
Some of you I know are working over there. Some of you are my students, so that's great. But we're over here in the more fun part of town, I guess, which means that parking is impossible and expensive. But we welcome. I want to make sure I send the word out. We welcome visitors, and we love to have people come over and see what we're all about. And we're having a lot of fun dragging people in. There's even been Jason sightings over at RIC, and Bob has been over there many times. So we welcome lots of visitors. And just to let you know a little bit about what's going on over at RIC, I think I have to click on this one. No, I gotta do this one. Is that going to work for us? No, maybe not. So, but the idea is a lot of work is going on in the rehab domain that has to do with basic science questions of neural control, how we move, and what technology can be brought into play to go on. So that's my plug, and I won't tell you about all of these things. This is just kind of to give a quick thing. So history, let's talk about history. So here's my favorite brand of car, but this is not the car I would buy. If I had all the money in the world, I would buy the newest version of this. But way back when, the Bugattis and even the Ford Model Ts, of course, had a lot going on with augmentation, and there'd been a lot of research and back and forth about exactly how you want to make this car turn. Should you do something like this with a stick, or should you do something like this? And all of this is body-powered control. So we have to begin with this idea of augmentation where you are extending the body's own power using mechanical work. And if you think about it, this is a pretty strange thing to come up with that would turn your car. And the reason why it's there is kind of an interesting one. If I have a joystick, for example, and I steer a car, it's not so easy, because if I turn the car by jerking my hand to the right, what does inertia do once the car starts turning? It's going to knock it back the way it's coming. And actually, if I do braking and acceleration with a joystick, it's actually another problem. And this is a huge problem in fighter planes and other things that actually do use joysticks, and they do a lot to get around this problem. But turning a car wheel is a little less of a problem when it comes to this issue. So wheels have become a pretty well accepted idea. I want to mention bicycles and airplanes too, because I think these are the real beginnings of all of these ideas. If many people already know, I think that the Wright brothers were bicycle engineers. That's how they came up. So a lot of their ideas for the airplane, which is a wonderful human augmentics device, I think, was a lot of technology on this was things like Bowden cables and other things. So I want to mention this idea of Bowden. Does people know about Bowden cables? So these are the cables that operate your brakes on the bike. And it's really one of the most amazing pieces of technology that's ever been invented for physical transmission of force. If you think about it, if you're building a gizmo, it is a very useful tool to get either motion or force transmitted from one place to another without trouble. So what is it? It's really a spring wound really tightly to make a tunnel, and then a cable that goes through it, and then you anchor both ends of the tunnel, and you can transmit linear force, right? So this is our brake lines, and it's been a big deal. And what's really ironic, and everybody should know this little fact, is that Sir Frank Bowden, who was really knighted after developing the Raleigh Bike Company and using Bowden Cables. By the way, Bowden is a street in England, and that's why they named them Bowden Cables. And that's where the Raleigh Bike Company started. But it turns out Raleigh gets all the credit. Raleigh and the guy who started the company, Frank Bowden, gets all the credit for the Bowden cable, even though he didn't invent it. So another guy invented it, Ernest Monington Bowden, did the patent, and then Frank Bowden made use of it in bicycles. But this is all happening turn of the 20th century, and then we had World War I, and people started coming back without limbs. And the interesting thing about that was that a lot of the people who really wanted to do something were either pilots or engineers, and they all were very familiar with this new technology being used on airplanes, Bowden cables and other things. So this is still, I would argue, pretty much the state of the art for people with amputations. I'll talk a little bit more about prosthetics in a minute, but this is a very powerful tool on a prosthetic limb, and all you have to do is connect something up to the healthy arm, shrug your shoulder whenever you want this cable to pull on something over here, and then you have a little transmission device. You can have it close the wrist, you can have it open things. And it's a great way for a person to have complete control over what's going on physically with a direct connection. And the interesting thing about it is that you can feel what you're doing. Okay, so I'll talk a little bit more about this, but this is the idea that physical transmission of what you're doing has to have some feedback. Feedback is a really critical issue, and if you don't know what you're doing, if you don't have a way of directly feeling or seeing or sensing, you're in big trouble, and you end up doing things like reaching for something and trying to put your arm right through the table because you don't even know what's going on. So here's some other neat stuff that's going on. So this is here in the Chicago area. Argonne National Lab came up with, in the 50s, came up with this wonderful remote actuator, and it all had to do with microscribes, or now I'm going to forget the name of what they're called, pantographs, I think. The pantograph idea of linkage systems where you develop connections of linkages so that you can transmit motion and force from one place to another. Maybe amplify motion and force depending on the geometry of this. So you can play around with tinker toys and other things to get the feel of how you want to do this. Everybody done the microscribe? Has anybody seen a microscribe where you can actually, or a pantograph where you can actually sign your name, and then another over here it'll draw it in much larger or much smaller form? So it's the idea of a kinematic remapping of what's going on. And I think that's neat. And here's a horrible picture, and now I'm going to forget the name of the company that came up with this first. But here's another example of direct body connection. Really what we're doing here is just changing directly what's going on physically. And we all know of people who, amputees who are using similar things. I would suggest that probably this may be the century where people start electing to have body parts actually taken off and replaced, maybe by artificial things to actually be better at what you're doing, right? This is the beginnings of the idea. So really, what do we have here? We have this idea of a control system. And for those of you who had control theory or have learned a little bit about control theory, this is going to look more familiar. But really, we have a human, and then we maybe have something we want to do. Here I say prosthesis mechanism, but really it could be anything, right? And then what we have the luxury of doing is putting in a controller. And when we put in a controller, we can kind of mess around with arrows on this thing. We can do things that could not otherwise be done. What I've been talking about so far is kind of these arrows, right? You're putting something through and just changing how it's directing. But I would suggest that the real element here that's important is feedback. Feedback is really amazing. And feedback can be done within the technology. So the technology is receiving the feedback and doing something. Or you can do feedback all the way back to the human and have the human receive the feedback. And that's a very powerful, and it's usually a little easier to do. But we also have things like the device itself dealing with it. And then we have the more classic way to do this, which is what we call control theory. This is feedback control theory, this red arrow, right? Is you're monitoring what's going on, and the controller is taking care of altering the behavior of this system. And hopefully you're getting some idea of the intent of the human. And that's very often the problem, is the human's intent is important to monitor, right? So this has started to happen, this idea of boosting power, maybe without the control part, way back when in World War II, we started to see it in the B-17s and other things. And that got to a point where it became the big selling point for automobiles as well. So power steering emerged and really changed what's going on. So has anybody ever played with two syringes? Next time you're raiding the medicine cabinet or you're in a doctor's office, steal some syringes. Connect them together. I'm sorry. So,
Not needles, though.
if you haven't seen this, the idea of what hydraulic amplification is all about is really fascinating. So you take a very small, 10 cc syringe, 1 cc syringe, the smallest syringe you can get, and you connect it to a larger syringe, right? And if you connect them together, fill them with water, or you can fill them with hydraulic fluid if you like. But what the idea is, if you push on one, you can really zing the smaller one, or you can push on the smaller one, and it's really easy to move the larger one, right? So you have this wonderful trade-off of being able to make things easier. You have to push it twice as far to get the same distance, but it's easier for the force. There's no free lunch, but the idea is that you can very easily and almost completely directly change the force-motion relationship, right? Which is really important, and that's really how power steering emerged. And then, of course, as soon as people started doing power steering, they said, let's do this with electrical signals. And that's where a lot of the trouble came in. Okay, so what you're doing now is you're kind of divorcing some of the direct contact. And there's really two big problems. One is you can, you've maybe lost the ability to get sensation of what is happening, right? You can't feel it. You can't see it. So you have to put that in too with electrical connections. And then the other problem is there's all kinds of dynamics and communication issues that make control much more complicated. And the biggest one is, of course, delay, right? But it has been done, and I should say this is the same guys out at Argonne. And what are they doing? They're trying to move things around, and more recently they're trying to disassemble stuff inside of a nuclear reactor. And it's a really interesting evolution of robotics and toys that have to do with remote teleoperation and connection. But then there's this idea of being able to use this in the areas of what's been horribly called human extenders. I didn't make up this term, but this is a really exciting field that basically languished. Died, and some of us who remember what was it, Aliens? I guess.
Yes, it was Aliens.
That was kind of the death of of the idea of human extenders. And I love this paper by Casaruni. Casaruni's a wonderful guy who's out at Berkeley, who's been working in this for a long time. But he really lays out why it's very hard to do this. And I'll talk a little bit more about the idea of what a human the challenges behind this, but it's not that people didn't do it. So, there's walking robots. I think it was in Avatar also. They tried to communicate this idea. But really, it gives you, first of all, the power to rip your own limbs off. So it becomes a really dangerous thing. And I can kind of look at this guy and think, doesn't look that confident in what he's doing there, you know. And so I don't know exactly how he was feeling, but it's a dangerous thing. But then the other problem is the instabilities that go along with all of this, right? You have this, and it becomes not only a difficult problem, but it can be actually mathematically impossible to make something like this work. And if you look at it from a control theory standpoint, but there is hope for this. Okay, so this is now. Does everybody know about IEEE Spectrum? IEEE Spectrum has really become a fantastic magazine. I'd say it's just as good as Scientific American for kind of putting your finger on new and emerging technologies and interesting hope. But this was a cover story in a recent issue, and this is the same group, Kazaruni's group, developing first a military application. This was the Bleaks robot first, but now is actually they have an offshoot company that's making the E-leg here, which is a really interesting idea. And yesterday I saw this demonstrated at RIC, and they just grabbed one of the patients who was a complete spinal cord injured patient, grabbed her, and in about an hour she had completely learned how to make this thing go. But it's a slow process, and it involves instrumented canes usually for doing this, or a person walking along and saying, push, make the right leg go, make the left leg go, make the right leg go. So there's a lot still to happen, but the really interesting thing that's happened in recent days is motors and sensors have become cheap and controllers have become easy, right? So it used to be you spend a fortune on the digital data acquisition and control system, and you'd buy motors that are ridiculously heavy. If you think about motors are made out of iron, and they're heavy, and they're problematic. So there's been a lot of great recent designs in that area. One of the big companies that's been working on this is Sarcos, which is a Utah company. It's actually part of an academic establishment at the University of Utah. And they've done a bunch of robots, including robots that walk and keep balance by themselves, but also these teleoperation systems where you can actually communicate. So what do we have here? We have this nice electronic connection, and this guy was operating the tool. And you can buy this device. The real final extension of this idea, though, is what happens when you get on a modern airplane now. Now, all of this stuff is taken care of in multi-redundant systems that help the pilot communicate with the flight surfaces. And this is really an important thing. There's also all kinds of drive-by-wire approaches that are coming out now, where you have completely separated the physical connection between the human and the vehicle or whatever else you're doing. So these are happening, and they're going to continue to happen, but there are problems, and we don't see them yet every day.
Jim,
Yeah.
Toyota, its pedal does not connect to the car. It has a transducer.
No, we don't want to bring up Toyota as an
And so
maybe we do. Yeah.
It's actually disconnected
And
mechanically.
and I think, is this the same pedal? I don't even know. Is this the same pedal that caused all the trouble? I don't think
I
it
don't
is.
know.
I think the Camry pedal was a physical connection. But we've gone electronic in a lot of areas, and it saves energy, but it makes life. It also brings in new problems, right? So there's also the electronic controlled Edinburgh arm, which came out in '73. So this is a while ago, but very interesting idea of using the electrical signals, of course, from the area in the stump of the amputated limb to communicate with the motors that are doing things. Now, why don't we see this every day? I'll talk more about this because there's been a lot of recent things, but why don't we see this every day? It turns out that this kid would start sweating, and then all of a sudden the electrodes are not giving you the same reading, and it can't adapt over time. Plus, it's a hassle to put on in the morning. So most people don't use these things. I'll talk a little bit more about prosthetics in a minute. So this is really the state of the art now, is this idea that you're getting the boosted power, but you're also getting boosted control. So I'm not an expert in this, but I do know that if you look at the flight surfaces that are moving during flight on one of these fancy new airplanes, and I don't have all of the fancy new airplanes on, but a lot of them, you'll see them moving in very strange ways when a person maybe just gives a command to go to the right. And that's because what's going on is not just that it's, power is being made easier, but also that the control system has become so sophisticated that only the control system really knows what to do to get the job done. The pilot doesn't know the math and or the transfer function, as you might say, for how to get a flight surface to bend in order to get a smooth turn to the right or something like that.
Yeah, I heard the stealth fighter is completely unflyable by human.
Right. Yeah, and I think it's actually important. I'll go back to this because I think the other thing that's important to mention is that what's really happening here is that it's unstable. The system is very unstable.
Right. Exactly.
So the controller is trying to restabilize the system, but at the same time, the pilot doesn't want a stable airplane. And if you think about it, that's an interesting question. I don't want my airplane stable because if it was stable, it would be less maneuverable. So they're constantly monitoring what's going on and adding their own human component to the system that just keeps it on the edge of stability so that it doesn't start rolling off and exploding, right? So, but it's an interesting thing. Very often we don't like stable things, even though we think we do. And I mean stable in the most perfect engineering sense. We don't like stable. We like maneuverable.
Well, plus, they're making shapes that shouldn't fly.
Yeah. So why is that? Why is that? I don't know.
Stealth, basically.
Stealth.
Yeah.
I think it's just so that they say we can do that. Right? So a little bit more about this idea of myoelectric control, just because I have guys that are down the hall. I don't do this really in my research, but there's a lot of people that are working down the hall on this idea. But the idea of bypassing the physical and electrical impulses and making something go. That's a nice idea. Myo meaning muscle, electric, you know what electric means. So wheelchair-mounted manipulators are an example of this. There's a bunch going on right now, but this is kind of an interesting other area in rehabilitation. This is rehabilitation robotics that I don't really do, but the idea of being able to control something that rides along with you, or maybe separates from the wheelchair. There's been a few of these. Separates from the wheelchair, goes to the refrigerator, gets you a drink, brings it back, kind of idea. So there's a lot going on with that, and of course the neural impulses come into play. This is our good friend Richard Weir, who actually gave me some of the good slides I had today too. This is the Bion, which actually was invented by someone here in Chicago at the Illinois Institute of Technology, Phil Troik, and was smart enough to say, what if you make an electrical interface capsule that's freestanding, and you get that FDA approved, and then you can put whatever electronic gizmo program you want inside of it. So that's what he did, and it's wonderful because it's solved problems now. But the idea is that you can actually inject this. It's big, but you can inject it with a syringe into your muscles, and you can actually have it read out what the muscles are doing, and it just stays there for the rest of your life. And you inject enough of them in, you can get a complete picture of what muscles are actually singing about all the time. So what is your intent? And then that's being used in this case to drive a motor for a prosthetic limb. And the way it communicates with the outside world is they have a magnetic induction coil sleeve that goes around the outside that kind of looks like a bracelet only. And then it communicates using magnetic induction with the outside world and tells everything what to do. So that's a neat idea. Another interface that's neat is this idea of targeted reinnervation. So a lot of people know about this already. It's been on the Today Show and been featured in a lot of places. And this is Todd Kuiken, who's really worked on this for about 25, 30 years now at the Rehab Institute, and made big waves with it. But it's the idea that you have the nerves in the stump of your arm, you take them and surgically re-implant them in your pectoral muscle, which you're not really using anymore, and fan them out, wait about a month, and they've reintegrated with the muscle. And the muscle actually can act as an amplifier of the electrical signal now that these nerves are there. And you put electrodes all over the pectoral, and then you start seeing what happens when the person thinks, flex the wrist. And you see activity in a certain area, you map that out, and you put that into a controller for the artificial limb, right? So what they found also that was interesting is that they accidentally solved the other problem. We call it extended physiological proprioception, EPP. This is the idea that you want to be able to sense what's happening, not just command what you want to happen. So you want to be able to feel that you've hit the surface you're aiming for. So what they've realized is that some of the areas here are sensory, they're not motor. And if you tickle them, you get a sensory that you can map out again. And the person says, hey, I feel like you just touched my thumb. That's very useful because you can use that as a channel to get information back. So what are we doing? We're closing this feedback loop that I talked about, right? So that's really important. And they've invented tickling devices for sending the signal back, and that's very exciting. There's also a variation of the Utah ray, which is probably the most significant invention for interfacing with neural commands in the last couple decades. This is a variation that's the slant array, and the idea for that is you can push it into the nerves here, and eventually one of these will give you one of these pins will give you a relevant signal. By the way, this is about half a centimeter square, this little device. It's really small. Actually, I think on the next slide I have it. So you can actually read out what the intent command is coming down in the nerve, which I think is very exciting. And then, of course, there's the full force application of this. This is the Kinetics, which miraculously was actually able to get FDA approval for this device to be implanted in your brain. So this is now no longer slanted. They push it onto your cortex in your motor area, which is right about here, over the area that you want to control, and then you think, and something happens, right? And what happens depends on how you hook it up, and of course people have hooked it up to robots and hooked it up to video games and to web browsers and other things. And it's actually been implanted in real people, and it's very exciting. And then as soon as they got FDA approved and they implanted it, we had one patient at RIC. Investors pulled all their money out, and that was the end of that. So it's now living on in a new name with a lot of the same people called BlackRock Microsystems, but they're selling it as a research tool. It's not a medical device anymore. It's very sad, but this is the world of high tech and biology. So what I want to do is shift gears. Maybe I should say, are there any questions on that stuff, or comments, or what have I left out? I don't know.
So over Christmas, I had a gentleman from Lockheed come visit, and he said they were working on direct neural stimulus with lasers as opposed to electrodes, because somehow they said electrodes really didn't provide sufficient resolution anymore, and they're shifting entirely to lasers.
So there are lasers, and actually lasers can actually be used not only to sense, but you can actually bounce them off of nerves to get readouts of what the nerve is doing too, which is interesting. So laser stimulation is an interesting thing, and then laser on the microscopic scale will actually move things and apply force as well. So it's a very, very interesting idea. And people who are studying the myofibrils in muscle, for example, is small enough where you can actually use it as like a tweezer to hold on to things. So yeah, lasers are very exciting. But of course, you have to get them near where you need to do the work, which means a lot of times you have to cut open the brain anyway. So that's one problem. But yeah, I think lasers are an exciting idea. And actually the other exciting idea is microfluidics, which is delivering neurotransmitters directly to a site as well. So you have little teeny tubes giving a little bit of fluid that's filled with neurotransmitter and exciting the neurons. So all of this is happening. Now there's a big European initiative for that, and it's called, I forget what it's called now. Anyway, so that's the idea. Now this brings up this issue of haptics, which I think everybody's been introduced to the term haptics now, and help me, is it Greek or Latin? Playing with Greek and Latin words, and it of course started with graphics, and then they said, what do we put in front of it to have it not be graphics anymore, but be haptics, right? So the idea is that you want to be able to have handheld interaction that's rendered artificially, right? So we play around with this quite a bit, and I'll show you in a minute how we play around with it in a strange way. But electric motors are really still the state of the art. I would say hydraulics kind of comes in second. If you want to get something done, there really are some nice cutting edge technologies that are trying to emerge, but they've been trying to emerge for a while. So I'm talking about shape memory alloys and electroactive polymers and McKibben actuators and all kinds of crazy things. But still, the best way to get the job done is an electric motor. It's clean and it works, and people have just been, it's like the bicycle, it's just been designed and designed and designed and perfected. Anyway, but the idea comes, there are some real advantages to electric motors that are strange. If you draw a plot of RPM, speed of spinning, versus the torque that it's able to create, it goes out really far to very high RPMs. We know, we've seen a lot of electric motors spin very fast, much faster than our joints move, for example. It goes way out and then it just drops, which is not what you'd think it would do. You'd think it would kind of, the faster you spin it, the less powerful it is, but it's not. It just goes way out and then just drops right off. Almost all motors are this way. So what does that mean? It means you have this incredible advantage at high RPMs. So if you have a situation where you're moving a lot, the advantage is really to take advantage of that. What you want to do is gear up your motor. Most people even in mechatronics don't even know this, but you have to gear up your motor, and that makes it a little bit noisy, and you have to build a gearbox. But what you can do then is you can get an advantage out of that. You slow it down, but you get this power advantage, and all you have to do is spin the motor faster. But the motor spins faster, it still has the same power output. So geared motors are still the best way to do that. But there's a huge price that you pay for that, and that's that you give an advantage to the speed or to the power, and you have a disadvantage going the other way. So when I interact with a robot, sometimes I want it to comply. I want to program this robot to move if I push on it. And then we call that backdrivability. And all motors and robots that have been invented to interact with the world up until about 1980 were not designed to do that. So if you go and find an industrial robot somewhere, and there's a lot of them, even in this building there's a lot of them, and you push on it, and if it's off, it won't move at all, right? So robots have been redesigned for haptics so that you can have the back and forth. And a lot of times what that means is you've gotten rid of the gearbox and you have what's called direct drive, or close to direct drive. So you don't get the highest torque, you don't get the highest speeds, but you do get backdrivability, okay? But there's still the other big problem of what we call closed loop telehaptics, right? The idea of I push on a robot here, and a robot at the space shuttle pushes on a screwdriver that's maybe turning a screw and screwing something in, and I'm able to feel that, exactly how that robot up there is interacting with it. And the problem is this idea of delays and dynamics. They're always there, and they're substantial actually with electric motors. If you think about what an electric motor is, it's a hunk of inertia that has to move. So it has a time constant. It has to ramp up. And so there's enormous problems with haptics, and it's a huge problem, and it's still not solved very well. There's very few applications that actually do closed-loop telehaptics, where you actually get the feeling back. In fact, the best-known surgical robot is a teleoperated robot, the Da Vinci surgical system, and there's no haptics in it at all. The surgeon relies on visual feedback to get everything done, which is okay because you're dealing with soft tissue. Soft tissue deforms like crazy if you push on it. So all you have to do is look and see if the tissue is deforming, and you know that you're pushing on it too much, right? So you slow down and you rely on vision. And that's a big problem. So there's also a whole bunch of fun things that we can do with interactions and haptic robots. So I want to talk about that a little bit here. And a lot of what I've realized is that if you want to study what's going on in the human body with technology interfacing, that you need to study biomechanics. And when you start studying biomechanics, you realize that you have to start studying, this is my career actually, you have to start studying the neural controller that makes the biomechanics work. And once you start studying that, you have to start studying learning, because that's how our neural control works, is we learn. There's a huge component of that. And once you start studying learning, you realize you have to start studying statistics, because that's how learning really happens. It's machine learning too. It's a statistical operation. And then once you start studying that, you really have to start studying things like psychology. So I think it's good you're going to go next, right? There's really no end to this, but you can understand this. We all end up as mathematicians in the end, right? So this is a horrible, busy slide, but this is meant to tell you that the nervous system is ridiculously slow. When I reach for my cup of coffee, I could use visual feedback to know whether I've reached it. I could use haptic feedback to know that I've touched it. I could use a lot of other things in my system to monitor what's going on, but the problem is the news gets to my brain too late. We just don't have the luxury of doing this for rapid movements. So how do we deal with it? We have a new mode that goes beyond feedback. We still have feedback, but we have a new mode called feed forward. Feed forward means I plan ahead. I base a lot of what I do on my experiences in the past. Well, what is that? That's learning, right? It's adaptation, or it's whatever you want to call it. In fact, I'm not going to get into a definition. I'd let the room argue about what is learning and what is adaptation, because you get everybody in a room and try to argue about that. So the other thing I want to talk about is what we do at the Robot Lab is we study these forms of augmentic interactions, right? And there's many different forms. So there's all kinds of fun stuff you can do to goof around with this issue, right? There's direct connections between two people, for example, or there's a robot assisted. So this is really three element agents here, right? Three agents working together. There's all kinds of fun stuff, and I just want to tell you about this. And then, of course, we've messed around with developing technology too. So we have all kinds of conceptual ideas that have emerged over time that are robotic technology to get the job done. But really, what it's about is the software. So you can have really simple robots like this guy. This is my friend John doing what we call what we call the manipulandum. And there's a lot of these in the world right now, but this was one of the first. And the idea was he's playing a cat and mouse chase game on the screen, just a video game, where you try to move to the target and stop. As soon as you do, there's a new target, and you move to that. And then we introduce this robot force that he experiences that makes him screw up. And it's a very simple formula that we put in, but it doesn't really matter what the formula is. What matters is that you can't draw your name anymore. You can't draw a circle. It really screws you up, and it's a lot of fun to try it. Actually, you sit down and you immediately want to figure out what this strange thing is. And it's a vector field of forces, so we call it a force field. This is a true force field, not like what you'd see in Star Trek, right? But this is really a force. What is a force field? This force field is a state-dependent vector field of forces, right? So So it doesn't matter what it is. Gravity is a vector field of forces, but you could have gravity slant sideways in this environment. Or you could have something like the Paris display that was developed here at AVL, combined with a nice big robot underneath and some tracking systems, and you can get really fancy with this, right? In 3D in a large workspace, but with very strange forces. And then we've done it also on the limb. This may be a video, I don't know. Is there a video? Yeah. So we developed one that was very specialized. It only worked on knee flexion. So you'll see it come on here in a second. And it's a thing we call the Sarcos, which is a device that, well, it's going so fast you can't see it. There it is. It's rendering, at one small instant in the gait cycle, it's rendering a torque to assist the person flexing their knee. So you can do all of these things. And then, of course, the big cute thing here says, please do not show to anyone, and I'm showing it. But it's the idea that you could also do the idea of teach and play with a robotic device. So the therapist is making this guy move, the robot is staying out of the way, but just measuring what it's being done to it. What happened? Maybe I lost the connection there?
That's your screen, right?
Yeah. Your calendar.
Oh, your
probably
calendar
came
came
out.
out.
There we go. Okay. Yeah, it's time you have to go to the faculty meeting. So the idea though is that you can have it just do teaching and playback. That's boring. That's not what I think would be something that you can do, because you can get a therapist to do that, right? So we played with the idea of what else you can do. So there's all kinds of stuff you can do with this interactive technology. And there's a long list of cool things, and I don't really need to tell this group about it, except to say, you know, one of the things that once you get down to on the list of novel ideas is this idea of distorting reality. So we talk about augmented reality and virtual reality. This is distorted reality now. And here's kind of the essence of it is you can actually take a person who's making this mistake. A healthy person would make the red line here, and a stroke patient actually made this line where they repeatedly made a mistake to the left. They can't reach in a straight line to the target. They eventually get there, but they have trouble. And then we take and magnify their mistake. Okay, so this is haptic now. The robot is actually pushing them and making their mistake larger. For hundreds of movements, they practice this. And then we turn off the forces, and we return them to the normal world, and they move straight. Now, this is straight, and you probably are wondering, do they stay straight, right? But what's really interesting is this is 75 movements after we've turned off the forces. So we've shown them kind of a new way to move by first making them worse, and then making it better. So this is the learning process happening here. What we think is going on, and we've been studying it for a few years now, is this idea of error augmentation. So this is how we branded it. We got there first, actually, I think. So we're trying to brand it, right? But the idea, you can try this. I won't torture you with this slide, but basically this is to show you that if you do it on a bunch of stroke patients in a controlled study, you can get statistically significant trends. So the real trick, though, is how do you do this, right? So I'm an engineer, and the first thing I think of is gain and offset. Those are the two things first linear transformations you do on things, because how do you magnify someone's mistake? How do you augment their error? And there's really a couple of ways we've thought about doing it. One is to amplify it, right? So that the gain, take the error, E, at any given instant in time, so this person's reaching and they're here, and we take it and magnify their error so that now it's maybe by a factor of 2, they're moved out to here, right? So that's one way to do it. Another way to do it is to record their initial mistake. That's this E0. And then play it back to them on top of their next movement. So we get an average, usually we take several movements to get an average mistake. And then we take, so now maybe the next movement, they're here and they're making that error. And, whoops. And we're adding E0 to that error, and they're getting out here. And these look very much the same, but the difference is one of these, as you learn, the error goes to 0, and you see the truth, which is that you're perfect. Here, even after you've learned for a while, you're still getting offset by an error. And because of that, the error signal's traveling back to the brain. And even though you're getting diminishing returns from your learning, you're still learning. And you can actually learn beyond where you're actually learning. So we took a look at this and did a study where we looked at how long it took you to learn something if you trained under these different conditions. So this is our control, and you can think of control as a gain of 1, right? So how long are they learning? This is the black, and we measure it, and it's about here. And then if we do a ×2 error augmentation, it turns out that you've cut the learning time in half, which is really exciting. Turns out the offset is really good too. So we ratcheted it up and we did it at 3.1 and really amplified the error. And we found that there, they've lost it. So what we think is going on is there's kind of a sweet spot in here where there is a realm of error augmentation, or a realm of distortion that actually works and your brain makes sense of. And maybe out here, this is what your brain is rejecting as an outlier, saying this is BS, right? Very exciting though, what we think. And I won't talk about it, but you get the improvement in error is also reflected of this as well. So we're testing this in a clinical study, and I want to just talk really briefly about a clinical study on stroke patient. So what if you really do this right, and you get a big, large workspace robot and a big display like Paris, and you take a therapist, this is an actual therapist, and a patient, this is not an actual patient, it's actually the grad student who worked on it. And the therapist is holding onto a tracking device, and that causes a cursor to be presented in front of the patient. And the patient has to track that cursor. Now we know where they're trying to get to, so we can measure their error and we can amplify it. And so we're using both forces and motion to do that. And this is actually we're getting a double display. I didn't bother to take out the stereo to make that video, or he didn't. But the idea is this is what they're seeing, is you're trying to move your cursor to match the hand there at all times. And then the therapist gets to choose what's going on, what the appropriate therapy for this patient is. And it's also really blinded, like a good study should be, because the rater, therapist, the operator, and the patient all don't really know what's going on. We don't know whether we've turned on the error augmentation or turned it off. So we did a controlled study, randomized on this. And this is Dr. Kenny and me that are working on this with a bunch of other people. What we have is this week, actually, we have our final patient. We actually broke the blind early, though, and found really good results. We're getting an advantage. Hello. Getting an advantage. There it is. This. I won't bore you with the formulas, but we're doing both visual and haptic error augmentation. In this controlled trial, and we're getting results that show the difference between getting error augmentation and not getting error augmentation over time. And I probably will skip over this. The other thing we've tried with this is what happens if you try to train a surgeon maybe to be a better surgeon. So this is another study that was recently presented on laparoscopic surgery maneuver. This is a difficult maneuver. If you're a laparoscopic surgeon, you have to stick a tool into a hole and then operate. So if I move my hand left, it goes right, and it usually goes right at a different scale than what I'm moving. And up is down, but in and out are the same. So 2 of the 3 coordinates are flipped. We called it the flip study because of that. And what we showed is that in a number of measures, the difference between beginning training and ending training, you can show a big advantage in error augmentation. So versus just practice alone. So I want to briefly mention this new study because I think this is neat. But what happens if you augment in a different way. Let's say you augment by adding viscosity to the system. And adding viscosity is really not that great because it feels like you're stirring soup. But what if you add negative viscosity? Something that can't be done in the real world, but you can do it with a robot. A robot can do this. It's easy. It's really easy. You just program in the opposite of what normally would be viscosity. What is viscosity? It's a force proportional to your velocity, right? And I say velocity meaning a vector. So what's happening is you're actually amplifying every movement. Well, you're amplifying the error, but you're also allowing a very easy practice environment that allows you to move around really easily, but also see your mistakes, and the mistakes are amplified too. And you don't have to tell people to do anything. They have the ability to freely explore and do anything they want, and they learn in the process. So it's been very successful, and we have a big grant that Felix Wang and I are working on now on this. So I want to just leave you with one last hanging thought. I want to go back to this idea of robots and motors and what is a good motor. And there actually have been the idea that muscles might be the best motor. So this is a this is actually a robot that has no motors. It has chicken muscle. No, I'm sorry, this one was fish muscle, I think. Yes, this one was fish muscle that actually made a robotic fish swim. So these are actually artificial muscles that have been activated using an electrical stimulator system to make this thing swim. And you can make a very lightweight, easy, and efficient system that works very well with it. So this is, I think, a very interesting direction for augmentics to go.
How does it smell?
I'll tell you this, it's the quietest robot in the world.
Oh, that's true.
Yeah. And it's smooth. Right. So anyway, I just thought I'd throw that in. Okay, thank you. I'll put this up and answer quick questions. I'm sorry I went a little long. Yeah.
Just really quick question. When I know it's not the blind is not done yet, but from the results that you found, did you see that there was better results from visual augmentation or error augmentation? What happened?
Yeah, that we get this question a lot, and I say I'm going to leave that for someone else to answer. So I think it's going to depend on the context. So if you're doing laparoscopic surgery, it might be different than if you're doing rehabilitation. So it's tough because I don't know if the answer would be, but we have not gone after that. We've shown that it works in both alone, and we've shown that it works combined, but they were different experiments on different motions. So to do a controlled experiment, I say it's a good question, but it's not a great question because we've got success. It's maybe a good master's thesis or something to try it, but we haven't tried it yet.
So I know we're short on time, but so next time you're to teach us again, what would make a fun, tangible, completable human augmentics physical project? Is the fish one, or?
Well, the fish one isn't human augmentics, maybe, but yeah.
Fish augmentics.
Yeah, maybe it could be. Yeah. I haven't thought about this. That's something worth thinking about. Yeah. I could probably come up with a bunch.
We should try to think about it.
Yeah. And I'm sure. So the other thing is, this world that we're working in is very flexible and open, and young, imaginative people coming in with great ideas is what we need all the time. So it's a great